Welcome students. We are back with another lesson. Here we have drawn the binding energy curve. In this binding energy curve, we have drawn the binding energy per nucleon against the mass number. Now, this binding energy curve reveals very important features. Consider your deuterium and your tritium. These deuterium and tritium are lighter nuclei. Lighter nuclei in the sense these have 2 nucleon, this has 3 nucleon, whereas the other elements have 6, 14, 18, 12, 16, 32, 56. So these elements, your tritium and deuterium, have less number of nucleons. If they have less nucleons, that means they are lighter nuclei. So from this binding energy curve, we can see that the lighter nuclei, like your deuterium and your tritium, they have less binding energy per nucleon. The next important point we can see is this binding energy curve. In this binding energy curve, we can see except for your helium, your carbon, your oxygen, rest all of the elements lie on this smooth curve. So I can also say this helium, this carbon, this oxygen are at a maxima point, as you can see in this. Whereas the one which are lying on the smooth curve like your lithium, your nitrogen and your oxygen. Can you see? There is a dip in this case, there is a dip in this case, there is a dip in this case. This represents your minima. That means your minimum point. So let us consider the one which are at the maxima, like your helium, your carbon, your oxygen. They are at the peak, as you can see, at the peak and at the peak. So what does this denote? Means they are at the peak. If they are at the peak, means they have a greater binding energy per nucleon. If they have greater binding energy per nucleon, that means they are highly stable. Fine. In comparison with your, compare the ones which are at your minima. Like suppose this blue line, consider this blue line. Lithium, your nitrogen, your oxygen, your lithium, your nitrogen, and your oxygen. These lie at the down peak, so they are at the minima. If they are at the minima as compared to your maximum peak, so what do you notice is that they have the lower binding energy per nucleon. If they have the lower binding energy per nucleon, that means these elements, nuclei, are less stable. That means if you give a small amount of energy, they will disintegrate. Fine. Next, from this curve is that your elements like your sulfur, iron, moscovium, iodine, these elements, can you see? These elements, okay, let us suppose this is 40, this is somewhere around 120. Okay, so the elements in the range of 40 to 120, like your sulfur, iron, moscovium, iodine, they are having your binding energy more than 8 mega electron volts. This line denotes your 8 mega electron volts. And can you see this element, this element, this element, and this element lies above this red line? That means they lie above this 8 mega electron volts. That means they are the most stable nuclei in your binding energy curve. Out of which, can you see this iron Fe56? This has the highest binding energy per nucleon. Its binding energy per nucleon comes somewhere around 8.8 mega electron volts. So what do you mean if they have the high binding energy per nucleon? If they have the high binding energy per nucleon, that means their nucleons are very tightly bound. Means there is a greater force of attraction taking place between the individual nucleons. So such kind of, or the nucleus of such kind of elements will be very stable, and it will be very hard to break their nucleus. Moving on, as you go beyond, what we notice is that the binding energy decreases. It decreases, consider it decreases up till this point. Okay, this point may be somewhere around 7.8 or 7.6. Okay, let us consider somewhere around 7.6 to 7.8. So the binding energy per nucleon decreases to 7.6 mega electron volt to 7.8 mega electron volts. And out of this one, the lowest one is the uranium. Right? For uranium, the binding energy per nucleon is 7.6 mega electron volt. Now, why is the binding energy decreases as we go beyond, or let us say, why does the binding energy decreases as the mass number increases? Now, the binding energy decreases because if the mass number increases means the number of the nucleons inside the nucleus increases, isn't it? So that means there will be more number of nucleons. That means such kind of elements are your heavier nuclei. Fine. These elements are your heavier nuclei. So heavier nuclei have more nucleons. If they have more nucleons means they will have more number of protons. That means as the mass number increases, the electrostatic repulsion between the proton, the positive charge and the positive charge also increases. If this repulsion increases, therefore your binding energy decreases, and it decreases till 7.6 mega electron volt. So what is a nuclear fission? The phenomenon in which a heavier nuclei or nucleus, generally the nucleus which has an atomic number greater than 230, that means the mass number greater than 230. All those nucleus which has a mass greater than 230 will be known as your heavy nucleus or heavy nuclei. When such nuclei splits into two smaller nuclei of nearly comparable mass, such phenomenon is called nuclear fission. Fine. So let us consider your uranium. This uranium has a mass number 235. If mass number is greater than 230, what happens? It is known as your heavier nucleus. So uranium is a heavy nucleus. So if it is a heavy nucleus, that means it has very large amount of protons and neutrons. Large amount of protons and neutrons means large amount of nucleons. If it has large nucleons means there will be there will be electrostatic repulsion coming into the picture. If electrostatic repulsion comes into the picture, what did we just discuss? The binding energy per nucleon decreases. So if the binding energy per nucleon of this element decreases, that means it is small. If the binding energy is small, what does it mean? It means such nucleus are unstable nucleus. Fine. So if your uranium, it is an unstable nucleus. Fine. If we trigger it with a neutron, can you see this small dot? If we trigger it with a neutron, so uranium plus one neutron. Okay. What happens to this nucleus when it absorbs one neutron? So the mass number increases to 236. When the mass number increases to 236, what happens? After this trigger, the nucleus of the uranium becomes highly unstable. If becomes highly unstable, what happens? The nucleon starts to oscillate. Okay, can you see? They are starting to oscillate. So what happens? The deformation in the shape of the nucleus is taking place. If the deformation in the shape of the nucleus is taking place, what does it mean? The nucleus is becoming unstable and it is slowly disintegrating into two daughter nucleus. One will be your barium, which has a mass number 141. The other one will be your krypton, which has mass number 92. Along with this, it emits 3 extra neutrons. Fine. Out of this 3 extra neutrons, it leads some extra energy. And that extra energy is how much? 200 mega electron volts. So a uranium 235, when it triggered with a neutron, it yields barium, krypton, 3 neutrons and a energy. This energy is denoted by Q, which is also known as Q value. So the Q value of this reaction is how much? 200 mega electron volts. Fine. So how much energy is released? 200 mega electron volt. So this is just one nucleus. Imagine if you consider 1 kg of uranium. If you consider 1 kg of uranium, okay, there will be how many? There will be so many nucleus. That so many nucleus will produce around 10 to the power 14 joules. How much energy your fission product will yield? Suppose this uranium is disintegrated into a barium and a krypton, it will result into 200 mega electron volt. So if I consider 1 kg of this uranium, how much energy I'm getting? I'm getting 10 to the power 14 joules. Whereas your pencil battery, in comparison, it gives us around 1 joule, 1 to 2 joules per second. Okay, 1 to 2 joules per second. Whereas your uranium, when it disintegrates, can you see? It is more than the crores. Okay, it is 10 to the power 14 times. 10 to the power 14 times of energy it is giving as compared to your barium. So can you imagine how much energy is there inside this nucleus? Fine. So what we have from this reaction is that when a uranium is triggered with a neutron, it disintegrates into a barium, a krypton and 3 extra neutrons along with some extra bind energy. This energy comes from the binding energy. Fine. Now look at this 3 extra neutrons. Fine. So what happens if there are more number of uranium atoms? Fine. Now suppose this is your uranium which was triggered by this neutron. When a neutron triggers this uranium, it yields your barium, your krypton along with 3 3 neutrons. This is your 1 neutron, this is your another neutron, this is your third neutron. Fine. Now out of this 3 neutron, if I consider 1 neutron, okay, let us consider one of neutron to be a lost, okay, lost neutron. But the other 2 neutron, what happens to this other 2 neutron? These 2 neutrons goes and strike another uranium nucleus, as you can see in this figure. If these 2 neutrons go and strike the another neutrons, what will happen? Again they will give out 3 neutrons. This one gives 3 neutrons. Again, if one of the neutron is lost, the 2 neutrons goes and strike another 2 neutron. In this case also it goes and strike another 2 neutrons. In this case the chain continues. Right? So when the number of the fissions taking place at each successive stage goes on increasing at a rapid rate, such type of reaction will be known as your chain reaction. Here 1 neutron has struck, so this in place triggered other two nuclear fission. Now, this is your first stage where one nuclear fission is taking place. In your second stage, can you see there are two nuclear fission is taking place? In your third stage, what you can see there are 1, 2, 3, 4 nuclear fission is taking place. And if it continues in this manner, such reaction will be known as your chain reaction. Fine. Such kind of reactions was predicted by Enrico Fermi in the year 1935. Okay. Now note, if the mass of the neutron, okay, there is a certain limit of uranium atom we take into consideration for such reaction. Okay, let us say we consider certain mass. What happens if we consider a mass which is greater than the certain mass? Okay, like there is a limitation. Suppose you are conducting a nuclear fission reaction, you are considering only a limited amount of mass. Okay, now if you consider uranium atoms more than this mass, okay, you take more mass as compared to your certain mass, what will happen? This chain reactions will continue. If this chain reactions continue, it becomes uncontrollable. Okay, this is known as your uncontrolled chain reaction, and this uncontrolled chain reaction is the underlying principle of your atom bomb. Fine. So there are two types of chain reaction. One is your controlled chain reaction. The other is your uncontrolled chain reaction. Your controlled chain reaction, the reaction can be in your chain reaction. The reaction can be controlled and maintained steady by absorbing the certain number of neutrons. Okay. In this case, not all of the neutrons go and strike the other nucleus. Some of the neutrons are absorbed, like in this case. They are absorbed in order to put a control on this nuclear fission. Now what happens when you lose this control? When we lose this control, when we consider more mass, when we take more mass into consideration, then that will be your uncontrolled chain reaction. Fine. So that's it for today's class. In our next class, we will discuss about your nuclear fusion. So what we have studied is your heavier nuclear undergoes your nuclear fission. What about your lighter nuclei? The nuclear which was having a small binding energy nucleon, they undergoes your nuclear fusion. So in our next class, we will discuss about this nuclear fusion, F-U-S-I-O-N. We will discuss about this nuclear fusion reaction. Fine. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again.